can start the presentation. We already heard a little bit about Risc 5 and some of the applications that we are looking at in terms of space. And we also heard got a lot of analytics and what is happening in CIT in India with respect to Risc 5. But what I'm going to be presenting may be something like a summary of what they already said, and I'll probably add a few more aspects of what is Risc 5, at least for the student audience that is here, so that you can understand why we are talking about Risc 5, what it means for the global community, and what are the highlights, why Risc 5 is being discussed so much in depth during this presentation. Cool. So we can go to the next slide. All right. So before getting into Risc 5, I think this is something that Dr. Cyril already mentioned. Risc 5 is an instruction set architecture, right? So what is an instruction set architecture? So like you get from the name, it is a set of instructions that a processor understands, right? So a processor or a microcontroller, which is a set of instructions that it understands. So if you wanted to add, if you wanted to subtract, if you wanted to perform some sort of logical operation, these are certain instructions that are going to be given to that processor for it to understand what to do, right? And what is its role in computing? So let's say if you have a processor that talks a certain language, right? The hardware speaks a certain language, your software speaks a certain language. You kind of link this together, and that language. So essentially, the software has to tell the hardware what to do, and this is the instructions. This is the format of instructions that are given to the hardware so that it can perform its role. And it kind of highlights the basic operations, the kind of data types that you have, and so on. Some of the key components that we have are something like opcodes or operation codes. These are a set of binary instructions that are essentially what the machine understands. Like we cannot talk to the machine in high level language. So a very low level language is what is used to program. And finally, it comes down to binary code that the processor will understand and then start executing instructions. So the hardware or the logic gates that are built into these processors will understand only these opcodes in binary format and then start performing the instructions that are required. Um, so the types of ISAs. Now you have CISC, that is complex instruction set computing, or you have RISC, so that is reduced instruction set computing. Now most of your PCs, let's say your Intel processors, work on something called as x86. Now this is complex instruction set computing, where the number of instructions that are present are quite vast. So you have a very large table, a very large list of instructions that you have to that are going to be used. And you also have Risc. Now, Risc, one example of Risc is ARM. ARM is also a reduced instruction set computing architecture. And Risc 5, which is what we're talking about today, is also reduced instruction set computing like you have it in the name itself. Now, ARM has been around for a very long time. ARM has been the industry leader when it comes to the architecture that is available on a lot of your systems. Most of our phones run off of ARM. Apple's chips run off of ARM. Qualcomm chips. You have Exynos chips from Samsung that run off of ARM. Today we are discussing about Risc 5 because we are starting to see a small change in trend. We are not going to see this trend change anytime in the near future, but we are seeing all of these companies, all of these large companies that I mentioned, slowly migrating over to Risc 5 based systems for at least small applications, or some of their processors are incorporating Risc 5. So we could see this we could see growing quite drastically in the near future, but it's not going to happen very soon. All right, so can we move on to the next slide? All right. So Risc 5. What is the highlight of Risc 5? Why is Risc 5 being spoken about here? One is open source. Now we know from our experience with Linux that people really like Linux because the amount of resources that are available, the amount of community support that you get, simply the amount of development that is happening on Linux is far more than you get for any other operating system or any other software that can be developed on, say, Mac or Windows and so on. The reason being, given that it's open source, a large community starts contributing towards the development. And that's similar to what we're also seeing in Risc as well. I think we skip over to the previous slide. Can we move back? Sorry, next slide, please. Yeah, not this one, the previous one, please. Yeah, okay. Right. Um, so it's open source in the sense that there's going to be a large community when it comes to the development activities that are going to be happening. And the reason this open source architecture is gaining popularity is because of the licensing fee. So, of course, when it comes to any x86 or ARM, if you want to use the architecture or if you want to use the cores, there's going to be a lot of licensing fee involved. Um, and of course, given that it is a reduced instruction set computing, we are looking at higher efficient. The systems that are being built with RISC-V are very thoughtfully being built with emphasis on efficiency, that is power efficiency, and also time efficiency. So we're seeing machines that are being built that can very quickly perform certain instructions that were not possible in the past. It is modular and scalable. So because it is open source, a lot of companies can also pick up this architecture, customize it according to their specific requirements. So let's say if someone wants to build a chip that is specifically meant to perform some sort of an image processing task, you will see these companies picking up open source cores or building RISC-V microarchitecture from scratch, where they pick it up, they do the customizations that they need by themselves, or they could have a few other companies like Sci5 or TensorTorrent and so on that are working on similar technology. So you could see people picking up this hardware, customizing it for themselves, and making sure that their chips are the most efficient for the task that they are interested in doing. Right. So it's modular, so you can plug multiple together, and scalable in the sense that you can customize and scale it. Now, industry adoption. When it comes to industry adoption, we're seeing RISC-V applications are being looked at in telecom sector. We're looking at it in automotive. We're looking at it in aerospace. Um, and industry adoption might take a little bit of time because we don't have general purpose processors available. Most of the applications that we're seeing in RISC-V are mostly used like very specific to the application. Like we have Western Digital that has been developing chips that can communicate with their NAND storages. But we still don't have a general purpose chip available. But the moment we have these general purpose chips coming out, we will see a lot of industry adoption as well. And of course, I already mentioned the community support. We are going to see, given that this is open source, a lot of community coming together, developing software, developing open source cores, say IDEs and so on, that will support the development overall. Can we move on to the next slide now? Okay. And now coming to the point, because we are talking about space, the need for an efficient processor in satellites or small satellites rather. And because we're in UNISEC today, most of us are going to be looking at university satellites and CubeSats. One limitation that we understand that we have in CubeSats is energy and space, right? The amount of space that you have in the CubeSat. So when it comes to limited resources, we know that the power that we're able to generate off of a CubeSat is far lesser than what we can do on a microsat or a larger satellite platform. And currently, as I mentioned, most of the RISC systems that are being developed with emphasis on power consumption. They're paying a lot of attention to developing systems that are efficient in terms of how much power they utilize for certain tasks, right? And so we also have open source cores that are currently available from companies like TensorTorrent, and these open source cores can be picked up. Chips can be made out of this, and any aerospace industry can actually pick this up and design it for a dedicated application. So let's talk about image processing. Let's say you have a hyperspectral camera on a satellite. You pick up an image. Most of our applications that involve edge computing can also be done on the satellite itself. You do not have to send all of this information that you're picking up from the satellite to the ground to be processed in a centralized center. So if we are seeing large applications where these open source cores are being put into chips, or even some IP cores, some cores that are not open source that are being put into server class chips, um, with a little bit of customization, we can make it capable for space, and we can see satellites that have very high power chips or high performance chips, even on smaller satellites or CubeSats that are performing applications uh, like you see on microsatellites and larger satellites as well. So can we move on to the next slide, please?
Sir, sorry for the interruption. So we are almost
Mhm.
at the time limit.
Okay, sure. I'll wrap it up fast. So the three reasons why most processors, so when we at anytime we're going to be looking at any architecture like the ARM, we're going to see, okay, fine, how expensive is it and how does it perform? If we see x86, we're going to say, okay, how expensive and how does it perform? But one other parameter that we start looking at when it comes to RISC-V is also design flexibility. So as I mentioned earlier, as cost is definitely coming down, and most of the systems that we are currently looking at being developed are high in performance. And design flexibility becomes a major part because anytime you have to approach say ARM for customization, depending on the scale of your customization, they could say yes, they could say no, you might not be able to customize at all. But with RISC-V, that customization is in your hands. If someone denies customization, you can pick it up all by yourself and customize it. Or you can go to these companies that already have cores and request for customization, and they're actually open to doing this customization for you. Okay, so I'm on to the next slide, please. Right. So when it comes to global scenario, the reason why RISC is actually picking up, this is something that most people might not bring up, is because of the geopolitical scenario that exists. Um, because most of these existing IPs that we have, existing cores that we have are licensed, when it comes to chip availability globally, it could impact availability in say the eastern regions of the world because of sanctions that could be put up and so on, which is why we're seeing Russia, China, and even India picking up RISC-V as a potential alternative to tackle any chip shortage that could come due to global geopolitical scenarios. So that is one thing that is impacting the growth of RISC-V. We also have a lot of emerging markets that are looking at cost effectiveness and you know places where customized, like if you look at India for that matter, given that we haven't gotten into the semiconductor industry as strong as a lot of other countries that we see around, RISC-V makes a really good entry point, like we're seeing with the Vega processor and so on. Everyone is kind of incorporating this new open source architecture as the starting point. So that's how we can see it impacting the global scenario. Okay, next slide, please. Right. Now, when it comes to challenges, we have integration challenges. Now that this is a new architecture, we are going to see challenges when it comes to integration in legacy hardware in older systems. We're going to see challenges where people are reluctant to migrate to something new because they've over years we've seen ARM and x86 kind of take up a large part of the market space, but RISC-V coming in new, migration may be an issue. There's also fragmentation because being an open source architecture, we're going to see a lot of people picking this up, making small customizations, and eventually we might see some incompatibility between multiple systems that are designed with RISC-V, which is where we have RISC-V International that kind of regulates this to make sure that compatibility is maintained. Then there's also tool and software ecosystem. So anytime a company, let's say Texas Instruments wants to put RISC-V in their MSP430 series, they're also going to have to start developing the necessary library support and the software support that is required to develop on these chips. So this is just one example, but we could see this happening in STM series. We could see this happening in any processor or microcontroller series where a lot of toolchain support, a lot of libraries and code support is also going to be required. So for it to pick up, for RISC-V to pick up, all of this has to be set up, and that's going to take some time. So that's a challenge. Okay, so next slide. Future prospects, just to skim through, we are going to be seeing advanced process architecture. We already see a lot of companies that are using Risc 5. They have hundreds and thousands of cores in chips already that are server class. We're going to see increased integration in AI and edge computing. As I mentioned, it's customizable. So if you want a chip designed specifically for AI applications, you can customize. You can make sure you develop it for this edge computing capability. Um, we are also going to be seeing things coming up in quantum computing, and of course, continued industry collaboration, because large organizations like Qualcomm, Samsung are all coming together and working together for this to develop a supply. We're going to see a lot of industry collaboration, uh, and with all of them working, this is going to be really good technology that's going to be developed, because all this time we had one industry pushing for certain architecture, but with the global community coming together, this could be the next big thing. All right, so that's all I have for today, and thank you.